Okay, so I wanted to show you two examples and to talk a little bit more about the energy contained, a potential energy of a configuration where you have all of the charge and a uniform charge density on the surface of a conductor versus when you have the charge distributed out throughout the interior. Now, I won't even say a conductor. Let's just use two spheres. One has charge density, constant charge density on the surface, and one has constant charge density throughout its volume. And the idea here is to show that the energy, the potential energy of the configuration where you have all the charge throughout the whole sphere, right, the volume, has a higher energy than if all the charge is on the surface. And this is a reason why all the charge doesn't just distribute itself in the volume of a conductor when you apply a charge to a conductor. It all stays on the surface. Okay. And we're going to have the same total charge for both situations. So I'm going to have one sphere. So I'm going to have a sphere with radius big R and total charge Q, okay? And this Q, I can write now, I'm going to have, this total charge Q distributed equally, let me just revise that. So, equally on surface. Okay, and so we have sigma here will be, of course, Q over 4 pi R cubed, right? Okay, that's sphere one, the red sphere, and then we're going to have the blue sphere. So we have another sphere with radius R with total charge Q distributed within the volume equally within volume. Okay, so that means I have a rho that is just the total charge Q over 4/3 pi R cubed, the volume of a sphere. Okay, so that's a constant charge density. All right, so we're going to calculate the energy, the potential energy in both of those configurations. Now the potential energy, right, is the potential energy, I'll just write in green over here. The potential energy is, I'm going to call that U, is epsilon naught over 2, epsilon naught over 2, times the integral of E squared d tau over all space, right? So we need E, and we need E everywhere. Okay. So let's do it. So let's calculate E for the red sphere first, and do the calculation for that guy first. Okay, so for the red sphere, we're going to use, of course, Gauss's law, right? So we'll have the red sphere here. The charge is all on the surface, right? So the sigma is on the surface here. That means that inside the sphere, right, inside the sphere of radius big R, there's no field because there's no charge enclosed, right? There's no charge enclosed, no field inside. Okay, because even though it's, you know, a sphere of solid metal, right? There's no charge. There's no field, which we expect for a conductor, but okay. All right. So what I'm going to do is put my Gaussian surface outside here, and I hope that's not too dark to see, and that will be a radius little r, okay? And the Q enclosed, of course, is just going to be for my red sphere, go back to red, so the Q, more red there. The Q enclosed for my red sphere is just, of course, rho times 4/3 pi r q. In other words, just q, right? Okay, because it's the total charge. Okay, and so I'm going to use those sort of interchangeably. I might just keep q and not worry about rho and all that, but anyway. Okay, fine. And then I know that E is going to be constant along the surface, right? Right? Constant along the Gaussian surface, so its magnitude is constant, and its direction is always along the direction of r hat, right? Okay. And so, and also dA, right? dA is also in that direction. dA is also in the direction of r hat. So E dot dA is just going to be the magnitude of E times dA. So I know that the integral, of E dot dA over our Gaussian surface, right, so I do that in purple. So I'm saying over the Gaussian surface here in purple, all right? That is, it's just going to be the integral E outside, bring the E outside, dA over that sphere, and we know that the integral dA just will add up to 4 pi times r squared, little r, because it's the surface area of the Gaussian sphere. Okay, so now putting Gauss's law together, right, we know that the integral E dot dA is q enclosed over epsilon naught. So putting it all together on this side we have E times 4 pi r squared, and on this side we have q over epsilon naught. So not too surprising, E is q over epsilon, or 4 pi epsilon naught r squared. Okay, now this is just k q over r squared. Okay, not too surprising. And of course this is in the, sorry, okay. This is in the r hat direction. Okay, all right, fine. Not that surprising. Okay, now let's do the integral for to get u, the potential energy. Okay, we have to integrate over all space. So that means that we have to integrate from r equals 0, right, all the way out to r equal infinity, and then all the angles, right? All right, so, but between r equals 0 and r equal big R, there's no field. So my E squared integral is, I don't care about that. So I'm really only integrating from r equal big R to infinity. Okay, so let's write U. So we're getting the potential energy. Okay, and we have U is equal to epsilon naught over 2 times the integral of E squared. And E squared here is K squared, Q squared over R to the 4th, and then d tau, right? Here's a d tau right here, and we know in spherical coordinates what that is. That's r squared dr. And then I'm going to say d omega. Remember, this is the solid angle. And it's just shorthand for sine theta, d phi. Okay. And then over here, I'm going to say we're going to pull some stuff out. So we have k squared, q squared, epsilon naught over 2. And then we have the integral from big R to infinity of 1 over r squared, right? Because we've got this guy, we'll cancel some of this. Dr times the integral over the sphere of the d omega, and we know that this is just 4 pi. So I'm going to bring that down. So we're going to have k squared, q squared, epsilon naught over 2 times 4 pi times the integral of I think I'm missing a minus sign again. I'm always missing my minus signs. It's not good. But I feel like I'm missing one right now. Let me look real quick. You're going to take a break. You can fast forward through this if you like. But I do feel like I'm missing one. Oh. Yeah, let me check my formula. I'll be right back. I gotta check. Yeah, chalk it up to it being right after dinner. I don't know. No, I don't have a minus 10 problem. Anyway, okay, let's do this. All right, so we've got r to infinity, and we have dr over r squared. And this integral here is minus 1 over r. Okay, okay, so we get k squared q squared epsilon naught over 2 times 4 pi times, we've got a negative sign out here, 1 over r between big R and infinity. This here evaluates to 1 over infinity, which is 0, minus 1 over r, which will cancel that minus sign, and so we're left with k squared q squared epsilon naught over 2 times 4 pi over r. Okay, now k is 1 over 4 pi epsilon naught, and squared is 1 over 16 pi squared epsilon naught squared, right? So just going to do some quick in my head algebra, and if you don't believe my answer, please go back and do your own algebra. But what I'm going to write down is this is q squared over 8 pi epsilon naught 1 over r, okay? All right, so let's remember that. That is for the red sphere. So we know that u, and I changed colors, didn't I? Now it's the pink one. All right, is q squared over 8 pi, 8 pi epsilon naught. Yeah, 8 pi epsilon naught r. I'm just double checking my algebra here as we go. Okay. Yeah, because I get 16 divided by 8. Okay. All right. All right. So that we've got that for the sphere with the charge. Okay. Now let's do it for the volume sphere, for the blue sphere, right? And gotta keep it on the time here. Okay. So I'm gonna get a new layer to do that, but we're gonna remember, or I'll write it down again on the next page. But okay. So let's get a new layer. Okay, so we have for the red sphere, U is Q squared over 8 pi epsilon naught 1 over R. Okay, now let's do the blue sphere. So the blue sphere, again, we're going to have the situation where we have a sphere of radius R. I got to pause the recording for a second because I got to tell my kids something. I'll be right back. All right, back. Anyway, okay, so now, and actually I want to make this sphere a little bigger, so I'm just erase this real quick, and we'll make it a little bigger. There we go. Okay. Now, there is charge inside this sphere, which means we can't just get the field outside. We have to get the field inside too. Okay, so let's start with getting the field inside, and I'll just go here to some purple, a little lighter, and we'll get a Gaussian sphere here on the inside of radius r. Okay, so we have our Gaussian sphere. That's where we use Gauss's law. Integral of E dot dA is equal to Q enclosed over epsilon naught. First thing I always do is Q enclosed. Okay, so Q enclosed is equal to, we have to integrate now because we have rho, right? So is the integral of rho d tau from 0 to the radius of our Gaussian surface. That's why I'm keeping everything in purple here. And so rho is a constant, so this is just 0 to r of d tau, right? And so this is going to just be the volume of a sphere of radius little r, right? So that's going to be 4/3 pi r cubed. And if you don't believe me, put in d tau and integrate up, okay? But that's what you'll get, okay? And of course, I forgot my rho. Hello, rho. Okay, there we go. We could have just guessed that, but there you go. Okay. Now, so now, and then E, of course, the usual, this guy here, we can pull the E out and we get the integral of E, I'm sorry, we get E times the integral of dA, which is just the surface area of our Gaussian sphere, 4 pi little r squared. Okay, so now putting it together, right, is equal to rho times 4/3 pi r cubed. Okay, and so now we can we're not gonna put in Q for this, right? Because the total Q is not contained in this Gaussian sphere. The total Q is once you have all of, if you surround a Gaussian sphere around the whole thing, right, then you have the total Q. But right now we don't have the total Q. So I'm going to leave things in terms of rho. Okay. I can't put Q in there, our regular Q that we said that was what all of the charges added up to. Okay. So now I'm going to say, what is E? Oh, I want my red color. Get more red. That's orange. Okay. So we want E. What am I doing? It's the blue sphere. E. Okay. E inside is equal to, so we should have said this is for inside. Okay, is equal to let's see, the 4 pi's cancel, right? And this will cancel two of these. So we get rho times r over 3. Oops, I forgot my epsilon 0 over there. Or epsilon 0, epsilon naught. Okay, there we go. There's E inside. Fine. And of course, in the r hat direction. Now let's do E outside. That's super easy because we've done this kind of thing a billion times. Here's our Gaussian sphere of radius r again, right? Okay. We know that we're just going to get as if all the charge was at the center, so it's going to look just like a point charge. So I know that E outside is going to be equal to Q, the total Q now, because I've got all of the Q enclosed in my Gaussian surface, the outer one. Okay, so that all the Q, so Q is actually just going to be KQ, right, over R squared in the R hat direction. Really simple. Okay, prove it to yourself if you don't believe me. Go through the whole Gauss's law thing. Okay, fine, but I am going to replace this Q with what I know, right? I know that the total Q, right? I know that the Q is rho times 4/3 pi r cubed, right? So I can replace that because I'm going to need to add things together anyway. Right? Okay. Okay. So now I need to do my integral. Okay. What I'm after is U. Okay. So U again is the integral. Whoops, sorry. I have to put my epsilon naught. Epsilon naught over 2 times the integral of E squared d tau over all space. Okay. Now we know that d tau is r squared dr times d omega, right? So we can write that out. So we have epsilon naught over 2, and I'm not going to put the E in yet. I have E as a function of R, right? So I have an integral over R, but I have to split it up because there are two different versions of E. One that's good for R equals 0 to big R, right? That's the inside. And then one that's good for big R equal big R to infinity. Right? So we have two of those. Oh, hold on a second. Finn! What? We have to go in like 5 minutes.
Okay. I just don't want to sit in the...
Okay, I heard you. Okay.
Yes, Daddy.
Okay, so sorry about that. Too much hassle to pause the recording and redo it. Okay. All right. Let's see. So we've got to split this up for inside added to outside. So we're going to go from E inside squared, right? and then we're going to be integrating our r from 0 to big R, right? R squared dr, and then there's going to be the integral of d omega, no matter what you do, and that's just going to be 4 pi. And then plus the integral for the outside, over 2, the integral e squared outside, r squared dr, and then 4 pi, because there's the integral of the d omega, and that's from r to infinity. So it has to be all space. Remember, it's super important. It's super important that it's all space. Okay, so let's do the integrals. All right, this first one, e squared inside, is going to be epsilon naught over 2. This one here is, and then it's going to be rho over 3 epsilon naught all squared, right? And then r squared, so the integral 0 to r of r squared, right, times r squared dr. Okay, oh, I forgot my 4 pi. Let's put the 4 pi there. Okay. And then plus the next one is going to be, let's see, k squared, q squared, and then epsilon naught over 2 times 4 pi. And then we have the integral from r to infinity of 1 over r squared, and then r squared. Something's wrong here. Oh yeah, I'm sorry. It's 1 over r to the 4th, duh. R squared dr, and I forgot to square things, I think. No, I'm pretty good. Yeah, because I got k squared, q squared, and then 1 over r squared. That's the only thing I forgot. All right, integrals away. This is going to be the integral of r to the 4th, right? Which is r to the 5th over 5. This is going to be the integral of 1 over r squared, which we know is minus 1 over r. So let's do it. So we have epsilon naught over 2 times 4 pi times rho over 3 epsilon naught squared. And then we have r to the 5th over 5 from 0 to r. And then plus k squared q squared 4 pi epsilon naught over 2. And then we have the minus. So we have minus 1 over r from r to infinity. Okay, doing these out, this is going to be just big R to the 5th over 5. So we have epsilon naught over 2 times 4 pi rho over 3 epsilon naught squared, r to the 5th, big R to the 5th over 5. And then the minus signs will cancel here because this will be 1 over infinity, which is 0, or minus 1 over infinity, which is 0. And then minus 1 over r, but there's another minus sign, so it cancels. Okay. So plus k squared q squared 4 pi epsilon naught over 2, 1 over r. Okay. All right. Now we have a bunch of work to do to put these two together, and I will be back in a sec to do that. Okay, so let's finish up this algebra. Okay, so we have a bit of algebra to do. So 1, do you see the row that's right here? So this row right here, this guy here, we're going to replace in terms of the total Q, right? So we can write rho is equal to Q over 4/3 pi r cubed, right? All right, so I'm going to replace that up here. And so I'm going to go back to my blue color, and I'm going to go here. We have epsilon naught over 2 times 4 pi. And then we have rho squared. So I'm just going to leave the rho squared over here by itself. So we're going to have q squared. And then we're going to have over 16 over 9 pi squared r to the 6th. Okay, and then I have I have this guy here, 1 over 9 epsilon naught squared, and then r to the 5th over 5. So that's our first term here. Maybe I should have done that in a different color here, but here's our first term here, and that becomes this. And now I'm going to do a little simplification before I write down the second term. Okay, so bear with me here. So we have 16 over 9, but we have a 1 over 9 here. So that 9 is going to cancel out. So that's gone. We have a 1 pi here and a pi squared there. So that's going to go away. We have 5 r's and 6 down here. So all these 5 go away and you're left with just 1 here. We have an epsilon squared on the bottom. So that goes away and gets rid of this guy. The 16 pi can be divided by the 4, right? So we have 4, and this will give me 4, right? Instead of 16. And so what I'm going to do is I'm just going to write the results of all this here. Now this 2 times the 4 is going to be 8. Okay, so what do we get? We get q squared, right? So that takes care of the q squared. We get 8 pi epsilon naught, right? So that takes care of the 2, the 4, the pi, and the epsilon naught. Okay, so what's left? We have 1 factor of r and 1 factor of 5, right? So we have 1 over 5 and 1 over r. Okay, good. So that's that one term. This term here, let's do that. I want to do that in a different color. I know we're kind of running out of room here, but let's do that in a sort of a brighter purple. Okay, so here, remember that let's remember what k is. K is 1 over 4 pi epsilon naught. So k squared is 1 over 16 pi squared epsilon naught squared. Okay, so I'm just gonna, instead of writing this, I'm gonna kind of do my algebra by erasure. Okay, and I'm gonna write, this is 1 over 16 pi squared epsilon naught squared. Okay, cool. So now I can do some canceling, right? This pi gets rid of one of these pi's. This epsilon naught gets rid of one of these epsilon naughts, right? This 4, you can, this 4 gets rid of, 1 factor of 4 and leaves us with a 4 here. And so we get 4 times 2 is 8, right? And so on this side over here, we get 1 over 8 pi epsilon naught q squared, q squared over r. Okay, good. So now our 2 terms, right? I'm going to get a new layer just to get our 2 terms, and I'll write them down again. Let's get the new layer. Okay, come up here. All right, so what did we have? We had we had u is equal to, let me do that in the right color. Sorry about that. So blue. U is equal to, we had 1 over 8 pi epsilon naught q squared over r, and then plus 1 over 8 pi epsilon naught q squared over r 1/5, right? Okay, so let's get a common denominator. The common denominator will be 5. And so we'll multiply this by 5, right? So we get, so in other words, let me be more explicit. So we're gonna, just to make the algebra, I'm gonna pull out stuff. 1 over 8 pi epsilon naught. And then we have, oops, sorry, I'm not done pulling stuff out. Okay, q squared over r. And then we have 1 plus 1/5. Well, I hope you know that's 6/5. Okay, so we get, this is equal to 1 over 8 pi epsilon naught q squared over r times 6 over 5, okay? All right, now remember, so this is u from the blue sphere. That's the sphere that had a surface, that had a volume charge density rho, uniform volume charge density, right? Okay, let's go back and just remember what the u for the other one was. I think we wrote it down here. Okay, here it is, right? So let's go back and I will just rewrite it up here. Sorry, cancel. Okay, and so u for the red sphere, right? Let's get a nice red here. So we have a surface charge density, right? So surface charge density here. So this is sigma. Okay. We had U is equal to 1 over 8 pi epsilon naught Q squared over R. Now notice this is greater than 1, right? This is like 1.2 or something like that. This is greater than this. So we have U in the case, so we have the blue U for the volume charge is greater than the U for the surface charge, okay? Then we can say this is a U rho, sorry, if I don't want to explicit U from a rho is greater than the U from the sigma surface charge, which is really why when you put a bunch of charge on a conductor, it doesn't just go and fill itself up in the, distribute itself uniformly through the volume. It stays on the surface because it is more energetically advantageous for it to do that. Okay. All right. So that's what I wanted to tell you. And then we have one more thing to cover real quick. It's very short. So I'm going to get a new layer so we can come off of this particular thing we're talking about. And we'll go to our nice yellow orange. Okay. Let's think about surface charge and the force on a conductor. Well, you can imagine that if you are inducing charge on a conductor, you might have a force between the two. But this is just really to point out, then we think we pointed out before that the electric field right above surface charge is just the surface charge over epsilon naught times this n hat vector. Okay, and we're not going to do a whole lot with charges. With forces between charges and conductors, but just to point out that if you want to know what the E is right above, you can get this. Now, what we usually use this for is to actually get sigma. Okay, so say for some reason you know what E is, you can figure out what is the surface charge that was induced, right? So this is the case where you'll have like a charge here, Q, and you've got some conductor over here, right? And this charge induces some negative charges on the surface, right? If that's a positive Q. And you'd like to know, what is the sigma? What is sigma? Okay. Now this is if it's completely spherical, it's really easy to figure out what sigma is. But if it's not, right, then it's harder. But you can actually calculate that knowing what the E field is outside, okay, using an equation like this. You can also calculate sigma from getting the potential. So if you know the potential, you just take the normal derivative. And we looked at this a tiny bit when we looked at the boundary conditions, okay? You can do that and find sigma as well. So if you get E or V, you can get the surface charge that's induced from those equations. Okay, that's the little tiniest thing I wanted to tell you. Okay. All right. I think that's all we're going to say for the rest of this section 2.5, and we'll see you for the next section of the book.